In this section, we will investigate vectors and their practical uses in science and in navigation. Hello, my name is Tom Atwater. Let's begin by looking at some basic concepts involving vectors. Magnitude and direction angle of a vector. The magnitude, which is the length of a vector u, which is equal to a comma b, is given by the absolute value of vector u, that is the magnitude of u, equals the square root of the sum a squared plus b squared. The direction angle theta satisfies the equation tangent of theta is equal to b over a, where a is not equal to 0. Let's take a look at an example where we are asked to find both the magnitude and the direction of a vector. Find the magnitude and the direction angle of vector u, which is equal to 3, negative 2. So, to find the magnitude, we use the formula that the magnitude of u, or the absolute value of u, is equal to the square root of a squared plus b squared. So, in this case, we have 3 squared plus negative 2 squared. 3 squared, of course, is 9. Negative 2 squared, of course, is 4. 9 plus 4 is 13. So the magnitude of vector u is the square root of 13. What about the direction angle? It has to satisfy tangent of theta is b over a. So tan theta is b over a, or negative 0.666 repeating. If we plug that into our calculator and do inverse tan so that we find theta, we'll find that the direction angle theta is equal to 326.3 degrees. Now, let's look at a diagram so you can see this vector, because it is important to understand, how did I come up with 326.3 degrees? Because I knew that vector u was going to be in the fourth quadrant. Because I noticed that the x coordinate was positive, the y coordinate was negative. So on the calculator, when I came up with what would have been my reference angle, I knew that I needed to add the 360 in order to come up with that final answer of 326.3 degrees. Well, let's look at the process for generating horizontal and vertical components of a vector. The horizontal and vertical components, respectively, of a vector u having magnitude, absolute value u, and direction angle theta are given by a equals magnitude of u times cosine theta, and b is given by the magnitude of u times sine theta. That is, vector u, which equals a comma b, is equal to magnitude of u cosine theta, comma, magnitude of u sine theta. Well, let's look at an example where we are asked to find the horizontal and vertical components for a given magnitude and direction angle. Vector w has magnitude 25.0 and direction angle 41.7 degrees. Find the horizontal and vertical components. So, here's a diagram of what that looks like. We have an angle of 41.7. We have the length of the vector, magnitude, as 25.0, and we want to find A, which would be the horizontal component, and B, which is the vertical component. So we use our formulas that tell us that the horizontal component A is equal to the magnitude 25.0 times the cosine of the angle. So cosine of 41.7. We multiply that out and we'll find that A is equal to 18.7. For B, we use the formula that it's the magnitude of the vector times the sine of the angle. So it's 25 times the sine of 41.7 degrees. That gives me an answer of B equals 16.6. And those are how to find the horizontal and vertical components. Let's look at an example where we have two forces applied in different directions and we need to find the resultant force, which is the sum of those two. Two forces of 15 and 22 newtons act on a point in a plane. If the angle between the forces is 100 degrees, find the magnitude of the resultant force. And here's a graphic to show what's happening. We have our two forces, 15 and 22, which are pulling on point P. You also see that we have our resultant force, vector PR, which is the diagonal of the parallelogram formed PQRS. So we can see that this angle Q is 80 degrees because the adjacent angles in a parallelogram are supplementary. That is, they add up to 180. And since this angle was 100, we know that's 80. In addition, we know the sides of a parallelogram, opposite sides are equal, so this is 22. So notice that we have 22, which is a side, 15, which is a side, and 80, the angle between them, which means we can use law of cosines to find the vector length V. So let's do that on the board. Let's find the value of the magnitude of V using the law of cosines. The way we set that up is to say that V squared is equal to 15 squared plus 22 squared minus 2 times 15 times 22 times the cosine of the angle between them, 80 degrees. That would give me V squared is equal to 594. And taking the square root, I find that V is approximately 24 newtons, since it is a force. Remember, this is a magnitude, so we should put our absolute value bars around the vector V to indicate that that's the magnitude. Well, now it's time for you to try a problem similar to the one that we just did. Find the magnitude of the resultant force of the two forces shown in the figure. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's find out how you did on this problem. Let me draw the two vectors, 60 and my 40, and the angle of 40 degrees between them. Now, the resultant force, of course, is the vector that would be formed by the diagonal of the parallelogram, which means that this side is 40, and this angle, which is supplementary with its adjacent, would be 140 degrees. So we would set the problem up that the magnitude of vector v squared is equal to 40 squared plus 60 squared minus 2 times 40 times 60 times the cosine of 140 degrees. And then, simplifying all of that, we would get the magnitude of vector v squared is 8,873.64. Of course, we have to take the square root of that and find that the magnitude of vector v is 94.2. And it's pounds, since that was what was originally given to us in the problem. Now, vectors have several operations which can be performed, and let's take a look at those. Vector operations. For any real numbers a, b, c, d, and k, vector a, b, comma b plus vector c, comma d is equal to the vector a plus c, comma b plus d. That is to say, you simply add the corresponding positions. The first two get added together, the second two get added together. When we're multiplying k times vector a comma b, you multiply k times each component, k times a and k times b. If vector a is equal to a sub 1 comma a sub 2, then negative vector a, or the opposite of vector a, is equal to the vector negative a sub 1 comma negative a sub 2. If we have vector a comma b and we're subtracting vector c comma d, then that's equal to adding the opposite of vector c comma d. So vector a comma b plus the opposite, the negative of c comma d. That gives us the vector a minus c comma b minus d. Now, a unit vector is a vector that has a magnitude of 1. Two very useful vectors are the vectors 1 comma 0, which has the letter I attached to it, and the vector 0 comma 1, which has the letter j attached to it. Let me write those down for you. So, I want to write that vector I is equal to 1 comma 0 and vector j is equal to 0 comma 1. And now we can take any vector, for example, the vector 3 comma 4, and I can write it as the sum of vectors I and j. It would be 3i plus 4j. So generally speaking, I can rewrite those vectors. For example, if I had vector a comma b, I can rewrite, or we can rewrite those vectors as the sum a plus I plus bj. So ai plus bj using the unit vectors. And that's true for the general vector ab. All right, well, the next thing I want to talk about is something called the dot product. The dot product is the two vectors. It's a real number, not a vector. It's also known as the inner product. We will see that the dot products are used to determine the angle between two vectors, to derive geometric theorems, and to solve problems of physics. So let's take a look at the dot product. The dot product of two vectors, vector u is equal to a comma b and vector v is equal to c comma d, is denoted u dot v. And I read that u dot v. Given by u dot v is equal to ac plus bd. Let's do an example of where we calculate the dot product. So, find the dot product of the vector 2, 3 times the vector 4, -1. So we do the dot product. Let me write down those two vectors, 2, 3, dot product of 4, -1. So we multiply 2 times 4. And we add to that multiplying 3 times -1. So 8 minus 3 gives me a dot product equal to 5. So it's as simple as that if you're looking at this saying, wow, okay, that's easy. In fact, it is. Let's look at some other properties of dot products before trying more examples. So we have properties of the dot product. For all vectors u, v, and w, and the real number k, u dot v is equal to v dot u. U dot, the sum of v and w, is equal to u dot v plus u dot w. U plus v dot w is equal to u dot w plus v dot w. K times vector u dot v would be equal to k times u dot v, and it would also be equal to u dot k times v. 0 vector times u is equal to 0. And, I'm sorry, 0 dot u is equal to 0. And then u dot u is equal to the magnitude of u squared. The following theorem that I show you relates the dot product to the angle between two vectors. So we have the geometric interpretation of the dot product. If the theta is the angle between the two non-zero vectors u and v, where theta is between 0 and 180 degrees inclusive, then u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. Or equivalently, we can say that the cosine of theta is equal to u dot v divided by the product of the magnitude of u and the magnitude of v. Well, that's a great formula, but let's look at an example so you can see it in action. Find the angle theta between the two vectors u equals 3, 4 and v equals 2, 1. So we want to use the dot product formula that we just looked at. So my two vectors u equals 3, 4 and v is equal to 2, 1. And we know that the cosine of the angle between them, the cosine of theta, would be equal to the dot product, 3, 4, dot 2, 1, over the magnitude of each vector. So, for the dot product, we would have 3 times 2, which is 6, plus 4 times 1, which is 4, over the square root for the magnitude, 3 squared, 9, plus 4 squared, 16, times the magnitude of our vector v. 2 squared is 4, 1 squared is 1. So what we have is cosine theta is equal to 10 over the square root of 25, which is 5. The square root of 5, we leave it as is. When we plug this into the calculator, we'll find that the cosine of theta is equal to 0.894437191. So cosine theta is equal to 0.894437191. And Plugging that into the calculator using inverse cosine, we get theta will be equal to 26.57 degrees. So there we have the angle between those two vectors. The law of sines and the law of cosines can be used to solve applied problems involving vectors. Let's try the following problem involving navigation. A ship leaves a port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far is the ship from port? What is the bearing from the port? Here's a graphic of the ship leaving port. So it's on a bearing of 28, traveling 8.2, and when it gets to that distance, it then turns due east. Now, what I'd like to do is show you how we get that 118 degrees inside of this triangle. So I'm going to redraw the north and show you that if I have this line, and of course it's parallel to this line, and that's cut by this transversal that's blue, then of course this angle inside here is an alternating interior angle with this, so that means this angle is 28 degrees. We know this angle here is 90 degrees, it's perpendicular. Hence, the 90 degrees plus the 28 degrees gives me 118 degrees. I have my two sides of the triangle, 4.3, 8.2. I have the angle between them, and that's what's going to allow me to find the magnitude of the resultant vector v, which is the red vector from P to E. So, let's get to it. Let's actually use the law of cosines to find the magnitude of vector v. So, I have the magnitude of vector v squared is equal to 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3 times the cosine of the angle between them, 118 degrees. So the magnitude of vector v squared is going to be equal to 118.84. And when I take the square root, which gives me just the magnitude of vector v, it's 10.9, which we will round off to 11 for our purposes. Now, to find the bearing, because that's the second part of the problem, we would use the law of sines. What we're interested in, actually, let me draw the picture of what we have going on here now. 4.3, this was my 8.2. We just calculated this to be 11, and we know this is 118 degrees inside of here, and originally this angle inside here is 28 degrees. And that was the original bearing, but now what we're interested in is this. In order to find that, what I need to find is this angle right here, and then add it to 28 degrees. So I will use the law of sines, and we will call this angle P, and I say the sine of angle P over the side opposite it, 4.3, is equal to the sine of 118 over the side opposite it of 11. When you work out all of that math, you will find that that angle P is equal to 20 degrees. But remember I said that that's just the angle inside of the triangle. We must add that angle of 20 to the angle of 28, which would then give us a bearing of 48 degrees. So bearing equals 48 degrees. So What that means is that it travels a total of 11 kilometers over the bearing or at the bearing of 48 degrees. Great job in today's lesson. Now, in this lesson, we investigated vectors and their practical uses with navigation as well as in science. We used vectors to calculate magnitude and direction, and we learned the various operations associated with vectors, including adding and multiplying. And finally, we learned how to use the dot product along with the law of sines and cosines to solve applications. Be sure to work the exercises that your teacher assigns, and we'll see you next time.